thank you very much for actually inviting me out. I've never been to Poland before. It's a great honor to come out here. Can you guys hear me in the back? Okay, okay. So how many people here know about the global interpreter lock? Okay, most people. Python and Ruby have one. Ruby 1.9 has one. More precisely, the C implementations of Python and Ruby. And one of the things that you might know about this global interpreter lock is it severely limits what you can do on multi-core machines, multiple processors. Sort of in theory, it restricts your code to only running on a single CPU. And because of that, it's sort of natural flame bait for people who want to get into arguments about concurrency, concurrent programming. You know, it's, oh, Python sucks because of the GIL, or you know, that sort of argument. And just to sort of to introduce this, I actually just wanted to start this off with a couple of experiments you can try to sort of see the effect of this global interpreter lock. So what I'm going to do first is this is just sort of a simple experiment of just a Python function that does a bunch of CPU work, just sits there and spins on the CPU. And one of the things you can do is just try it, you know, just say, okay, I'm going to call that with, you know, 100 million, see how long it takes. And then I'm going to do the same thing with threads, subdividing the work. You know, you sort of said, I'm going to have two threads that do half as much work. For the Ruby programmers, here's the same thing. I've actually tried this both in Python and Ruby. So two threads. And because of this global interpreter lock, there's a certain expectation that you have. I mean, essentially, because of this lock, you know that there's not going to be any parallelism. You can't take advantage of multiple CPUs. The two versions of code actually do the same amount of work. So your expectation is that they're probably going to run the same. But because of this lock, you can't use multiple CPUs. And if you try this out using, you know, like Ruby 1.9 on my Mac, you actually find that that's true. It's basically the same. You run sort of the sequential code, and it takes about 2.5 seconds. You run the threaded code, it takes about 2.5 seconds. You try the same thing in Python. It's not quite the same result. We're going to talk about why in a second, but you run it, you run the sequential code on, and you get like 6 seconds, and you run it with threads, and it's like 9 seconds. I mean, you take it's like a 50% performance hit just doing that. So one of the questions that comes up is like, why? Like, why did it get 50% slower because of this lock? Now, because everybody here is a Windows programmer, I thought I would try this on like a different machine. You know, maybe, you know, Windows Server 2008 is obviously my personal choice of machine here. So I tried the same experiment, you know, on that, and Ruby is basically the same. And go to Python, and it's an even more interesting result, right? So you can look at that and say, it's like from 7 seconds to 63 seconds. I mean, it's like, why does it get that much slower? And I'm not going to accept as an answer that it's Windows, okay? I mean, Windows is many things, but it's not that bad. There's something going on, something there. Yeah, very bad. I apologize to the Python programmers. I heard that you got a little bit of abuse yesterday, and helping that. So now we're going to talk about Ruby for a second. So that's one experiment. It's there's that. Another experiment you can try is just something with messaging. I did an experiment where I set up sort of client and server sending size prefix messages to each other. If you've ever used something like 0MQ, this is sort of a very minimal version of that. I mean, you're sort of sending messages back and forth. So here's some pseudocode of just a little test. I've got a little server that's just receiving a message and then pinging it back, you know, basically echoing it back. I have a client that sort of sends messages, receives a response, and because I'm not trying to be evil here, I decided to throttle it down a little bit. Okay, so it's the client actually sends and receives a message and then sleeps for a little bit. Mainly, I didn't want this to be like a messaging stress test. I just like, okay, send a message, get a response, hang out for a little bit, and then do another message. So this is another test that you can try. And then what I did is I did a little benchmark where I'm just going to send 1,000 messages back and forth on two scenarios. One is where the server is just unloaded, nothing going on. And then the other one where there is a thread running, so a CPU-bound thread competing with this server. And if you try that, You also get some interesting results. So this is what you get if you just run this messaging test with no threads. I actually threw C programming in here just as a baseline to see what the performance is. And what you see is that C, Python, and Ruby basically the same. That should actually be expected because you're not really doing any calculation here. You're just doing I/O, and Python and Ruby work fine for I/O compared with C programming. So you get that. If you throw in that CPU-bound thread, though, things just get kind of really wacky. I mean, you look at what happened. Well, C, for reasons that I don't want to talk about, actually got faster having thread thrown into the picture. Okay, that's a little bizarre. Python took about a 10x performance hit, and Ruby took about a 30-time performance hit just having that thread. So you can look at that and you can say, that's kind of curious. Like, what is going on? What's going on there? Just in the interest of disclosure, Ruby threads have this ability to set a priority on it. I tried to set the CPU thread with the low priority, just in case you were wondering about that. Okay, so that's a little bit curious. And then just to try a different experiment, I moved this over to a Linux configuration. This is an 8 CPU Linux machine actually running on EC2, so Amazon EC2, a lot of memory. Tried the same test. You actually get a much more interesting result there. C, about the same. Python actually did much better. It was only 1.4 times slower there. Ruby ran about 5,000 times slower. Okay, so you look at that and say, why? Like, where did that come from? I mean, where is like a 5,000 time performance hit coming from on like a big Linux machine with thread? So, and then there's some other things that get kind of interesting about this. It turns out that if you try some of these tests, by disabling your CPU cores. Actually, I don't know whether like on the Mac people knew this, but there's like an optional thing that you can install. It comes with Xcode, I think. This processor preference panel. You can actually come in here and like disable your CPUs if you want. So you can turn off the CPUs. So what you can do is you can run these tests. You can say, okay, I'll actually run one of these just so you can sort of see it in action. So this is code that's running the sort of the CPU test. Okay, it's like taking about 7 seconds to go sequential. Now it's running a threaded version of that. Pause for a moment here. Okay, so it's taking like 11.5 seconds. If you come in here and you disable one of your CPUs, and then you run the same test again, what you'll end up finding, hopefully, this is always famous last words for a talk, the whole point. You'll find that the threaded version actually gets better with like one of the cores turned off. Okay, I got like nine seconds. Another sort of mystery that you get with this. I mean, okay, let me turn the core on. You can do this sort of test. What I'm going to do here is I'm just going to put I'm going to put Python into an infinite loop. Okay, so this is like an interpreter running 100% CPU on the machine. I'm going to come back over here and I'm going to run the same test. Okay, so now my machine is like 100%, like 200% loaded. I have one spinning on in another interpreter, and now I have like this one operating. See what happens here. The threaded version even got slightly faster. Okay. So you can ask these questions like, why? What is going on here? I mean, it gets better with like more load, with less CPUs. And then also the Ruby one gets affected by that too. It turns out on my Mac, if you turn off all the cores and then you run the messaging test, it goes like 4 times faster. Okay, so that's a little bit mysterious. And then there's some other things too. If you downgrade versions of these interpreters, the performance is better. So like if you upgrade to Python 3, the messaging test actually runs slower. If you downgrade to Ruby 1.8, the messaging test gets better as well. So there's sort of this negative point for progress here. So what's happening is that essentially this GIL it actually does far more than just limit you to a single core, it actually has these very bizarre sort of corner cases where it's like it's making performance significantly worse. You get these sort of interesting effects. It's like, getting better performance by disabling cores. Like what's that 5,000x performance hit on Linux? Like, why is that happening? And I think one of the things that you might care about here is just, is really this question. I mean, do you have to abandon Python or Ruby to do concurrent programming? Like if somebody looks at this and they say, this is horrible, don't even use these languages for doing that. I mean, that's a question you can ask. I think another thing you could just think about is, maybe it's okay to have a global interpreter lock if it was sane. That's kind of my position, actually. It's like, well, okay, this lock, it kind of sucks, but if it was there, at least maybe it won't kill performance. And just as an analogy of that, operating systems running on a single processor usually work okay. I mean, they did the last time I checked anyway. I mean, they didn't worked fine. So there is that. Just another reason why I actually care about this. I think this is actually a cool little systems project. I used to be a university professor teaching operating systems, which meant that I got to make people cry with like synchronization problems on exams and talk about dining philosophers and things like that. And so this is sort of an interesting question of like, well, how do you make a better how would you make a better lock? What's going on? Why is all this weird stuff happening? And so it's kind of a fun little project. And then just as some background, this is more for the Ruby programmers here. I've actually been kind of talking about this in the Python world for about 2 years. So I gave some talks in 2009 about this, and mainly talking about some performance issues with the Python lock, and it just generated this huge buzz about, oh, can we do something better in Python? And just for this talk, I've actually looked at the implementation of Ruby as well. So I'm going to have some Ruby numbers and talk about what's going on there. Just in the interest of full disclosure, I'm not a super experienced Ruby programmer. It's kind of odd. I'm looking at the C code for Ruby, thinking, oh, this is kind of cool. But if you asked me to whip up a Ruby script, I'd just be dying up here. Okay, so just sort of know that my background is more in Python. So what I'm going to do is actually kind of take you through what's going on in both of these languages, because they're actually quite similar to each other, and the reasons for the performance problems are actually very similar as well. So I'm going to talk about the two global interpreter locks. And just to start that out, Ruby and Python are actually very similar to each other in how they're implemented at the moment. If you program with threads, it turns out that they are real system threads. They're P threads, POSIX threads, Windows threads. That's actually a misconception that people have sometimes about Python. They will say, oh, well, Python doesn't have real threads, or it's doing some weird, thread thing. That's actually wrong. It's actually using POSIX threads. They're fully managed by the operating system, and you actually do get concurrent execution of the Python interpreter. I mean, that's what's happening underneath the covers, and the same thing is happening in Ruby 1.9. as well. I mean, it's using system threads, P threads, and so forth. Also, one little bit about Python, this is more just history. Python has actually had threads since 1992. So this is like the implementation of this in Python is actually really quite old. It's almost had threads for 20 years. It's just that people haven't really given them a lot of love until recently. So it's been there for a while. But in both implementations, essentially what you have is this, this so-called GIL, this global interpreter lock. And really what this is it's just a lock that prevents one thread from using the interpreter at a time. And a lot of this is actually historical baggage, if you will. I mean, Python in particular, it was not written to be thread safe. It's a bunch of C code. It was never written to support threads. There's a lot of low-level details concerning memory management, internal state, C extensions, frankly, it's actually very difficult to think about how to make that fully multi-threaded. And to get around that, what they do is they essentially put a lock around the interpreter. So it's like, if you want to run in the interpreter, you have to have this lock. Protects the interpreter from seg faulting, essentially. And as far as I understand, that's sort of a similar thing with Ruby as well. I mean, it's like taking the C implementation of Ruby, making it fully multi-threaded without a lock is actually a fairly challenging problem. So now, underneath the covers, I don't really want to spend a lot of time on this slide, but the GILs in Python and Ruby are actually implemented slightly differently. In Ruby, it's the global interpreter lock is actually just a simple mutex lock. So pthreads mutex. Python actually has a slightly different implementation based on what's known as a condition variable. What happens in Python is that this lock actually involves a lot of signaling between threads. There's these operations like wait and notify, where if somebody wants to acquire the global lock, they have to wait for it, and then they get signaled by another thread when they get it. Okay, so it's a slightly different implementation, but the overall outcome is essentially the same. If you program with threads, essentially what you get is a kind of a cooperative multi-threading thing happening, where each thread will essentially run until it blocks. Now, blocking, that could be any number of things. Usually it's like an I/O operation, like reading on a socket, reading on a file, waiting for somebody to type on the keyboard, that kind of thing. So a thread will run until it blocks, and then when it blocks, it essentially releases that lock and says, okay, somebody else can run, and at that point another thread can take over. So what happens is the threads sort of cycle between each other, releasing and acquiring this global lock. And it's heavily tied to sort of I/O operations. And if you're doing I/O, one thing that I should say is actually threads work pretty well for that. There's a lot of, people obviously will look at threads and think, well, I hate threads, you should never use them. Turns out that threads actually do pretty well if you never do any work. Like if you're just shoving bits around doing I/O, you can have, hundreds if not thousands of threads on your machine, and it will like hold up and not crash. The problem arises, though, if you want to do calculation. Okay, so if you want to use your machine to actually do something, actually Fibonacci numbers seem to be very popular recently. If you have been following the Node.js rant online there, so maybe you want to do Fibonacci numbers, or you want to my favorite Fibonacci numbers, or image processing, or audio processing, or parsing, or something like that. The CPU is going to get busy doing that stuff, and the problem with doing CPU work is that threads that do things on the CPU don't give up the global interpreter lock. Essentially, they're just going to run until they're done with whatever they're doing. And so what ends up happening is both Python and Ruby have to do something to get these CPU threads to give up the CPU. Otherwise, they're just going to hog the machine. So the approach that's taken for this is essentially to run for a little while and then to forcefully cause a thread to switch. The way that this is done in Python is that the interpreter runs 100 instructions and then releases the GIL afterwards, and then reacquires it. In Ruby, you've actually got a little timer that runs in the background and forces a preemption every 10 milliseconds. So what happens in sort of the Python world is that if you have a thread that's just going to sit there, computing the 2000th Fibonacci number or something like that, it will run for 100, basically 100 instructions, give up the GIL, run for another 100 instructions, give up the GIL, and so forth. And kind of the thinking is when it releases this lock, other threads can kind of jump in and run there. And then Ruby is sort of a similar approach. Essentially you have a timer thread kind of sitting in the background. When that time slice expires, it forces whatever's running to release and acquire the GIL again. Okay, so it's a very similar approach, just a different implementation of how it's done. And in both cases, it turns out that the code to release and acquire this GIL actually looks a little bit like this. This is sort of greatly stripped down, but what's happening is in the interpreter you have some execution loop. It's running your code, running your Python or Ruby code. So it's running sort of virtual instructions. At some point, that gets preempted. It's either by that timer scheme or by that instruction counter scheme. And what happens is you get this sort of GIL release, GIL acquire step that gets thrown in there. It's kind of like, I'm going to run for a while, and then when I'm forced to give it up, I'm just like, oh, just release the GIL, go on with what I'm doing there. And so, the question that comes up, and actually kind of the meat of this talk, is actually on this little fragment of C code. This happens both in Python and in Ruby, that you have this release of the lock, acquire of the lock. Turns out that is the source of every performance problem that I presented in the earlier slides. I mean, if you want to know, like, why does Ruby run 5,000 times slower on Linux with that benchmark that I did, it's that. That's the reason for it. If you want to know why Python runs slower on Windows, it's that. So I'm going to kind of talk about sort of why that's a problem, or sort of what is going on under the covers. So just to kind of shine light on that. So essentially what's happening is imagine that you have two threads running on your machine. Okay, you have thread one that's running. You have thread 2 that's waiting. What's going to happen here is this thread one is going to run until it's forced to give up the GIL in some manner. Now, one way that it could do that is to do an I/O operation. It could say, oh, I want to read from a socket. If that happens, it's going to release this lock, and it's going to go to sleep, and the other thread will run. If that's what's happening, life is great. Okay, it's just, oh, I'm going to give up the lock, another thread will run, everything is cool, essentially. The tricky case is this situation where a thread never gives up the GIL. So let's say this thing is just running and running and running. It's computing Fibonacci numbers to no end, of course. At some point, it's going to get preempted by the interpreter. It's going to say, okay, you've run enough. Your 10 milliseconds is up. Your 100 instructions is up. And this thing will release the global interpreter lock. And you get this question now of what happens now. So the question is, which one of those threads is going to run? If you're an optimist, which you shouldn't be, you will assume that thread 2 will run. This assumes that this is like playing fair on the playground. It's like, okay, you got to share your toy now with the other kid. So you give up the GIL, the other thread will run. That assumption is not very good, actually. One of the things that happens on multi-core machines, and this actually happens quite a bit, is that this thing will release the global lock. And then because there are multiple CPUs, the operating system basically carries both threads forward at that point. It's kind of like you have a thread waiting on a lock. This thing will release it. And what ends up happening is you end up with like a timing, almost like a race to get the GIL. And what happens is the first thread might immediately steal it back, where it's like, oh, I'm giving it up. Oh, I'm taking it away again. It's like, I see this behavior with my toddlers a lot. It's like, oh, here's the toy. No, I want it back right now. So what ends up happening is this thread 2 may try to get this lock, but it just doesn't succeed at it. So one of the things that happens is that this code that you see in Python and Ruby, that doesn't actually do thread switching. It might do thread switching, but it doesn't necessarily. It actually depends on like what operating system you're on, number of cores that you have. Is there any kind of like scheduling priority with that lock? What's the operating system doing with it, and so forth. So that doesn't actually switch threads. There's some little hacks that you might see. Sometimes you'll see people do this kind of thing, like, well, I'm going to release the lock and I'm just going to sleep for 0 seconds with the theory that, oh, I'm calling into the operating system and it will switch. That doesn't work. Another thing that you might do is try to do things with the scheduler, like I'm going to release the lock and then I'm going to tell the operating system scheduler to yield. That doesn't work either on multi-core, because what you're really getting here are sort of conflicting goals. What's happening is that Python or Ruby is saying, hey, I want to run on a single CPU. I'm not thread safe. I have this lock. I only want to run on one CPU. The operating system is looking at this from a different point of view, saying, oh, I've got 8 cores. I'm going to run everything simultaneously. The operating system is saying, ooh, cores. I love cores. I'm going to schedule stuff. And what you end up getting is that threads fight with each other in various ways. And so this is actually what's happening on the Python side. Like if you go to Python 2 and you want to know, like, why does it get like 50% slower or twice as slow running with threads? What's actually happening under the covers is that this thread is running. Every 100 ticks, it signals the other thread saying, okay, you can run. But what happens, because you have 2 cores, the original thread just steals the lock back. The other thread wakes up and finds that the lock is gone. So that it actually wakes up and says, oh, the lock is gone. I got to wait for it again. So what ends up happening is this second thread in Python will just sit there and churn on like millions of failed lock acquisitions. And you can actually sort of see that, that effect. If you run with like 2 CPU threads in Python, your machine will actually be using like 150, 140% CPU load. And you kind of, if you look at that, you're like, why? Like, why is it using 140% CPU? Because, you know, there's this lock. Why is it using like a third of the other CPU to do something? Turns out that what that is it's the other thread just churning on like millions of system calls, basically being woken up, not finding the lock, and going back to sleep again. So it's just like wake, sleep, wake, sleep, wake, sleep, and so forth. And part of the reason why this is a problem in Python is that this 100 ticks in Python, if you do a timing of that, at least for many things, that might only be a few microseconds. So what's happening is Python is essentially releasing the lock every few microseconds, and the system is just slamming the operating system with operating system calls. So that's what's happening there. Another thing that's happening, and this is more related to the messaging example with I/O. It turns out that if you have a thread that is just sitting there hogging the CPU, and another thread wants to get the lock because of I/O, like a packet arrives or you hit a key or something like that, it actually turns out to be really hard to get the lock away, because what happens is you get this like a network packet that comes in. This thread will then just say, hey, I want the global interpreter lock, and this thread that is running will release it, but then steal it back right away because of this sort of timing thing. And what ends up happening is this other thread the I/O thread can just sit there stalled, making hundreds or thousands of requests to get the lock. So how this actually manifests itself is sort of very poor response time in I/O handling. I mean, that's what's happening there. And so if you want to sort of know what is happening on like that Linux machine with Ruby, I gave this benchmark where if you had no threads, it was like 1.18 seconds. And if I throw one thread in there, it goes to like 5,800 seconds. What's happening there is that the I/O thread, the thread that's doing messaging, just cannot get the global interpreter lock away. I mean, it's trying to get it, but it just cannot get it because there's multiple cores. The CPU thread is constantly getting the lock. Another thing that's happening here, which I'll talk about in a second, is that locks in Linux do not have a notion of fairness. What I mean by that is they do not give the lock up in the order that people want it. So what ends up happening is that lock just never gets given up. Ruby is just sitting there retrying like every 10 milliseconds to get the lock. So it's saying, oh, 10 millisecond, 10 millisecond, 10 millisecond, and it's just failing most of the time. So actually, to kind of say something about this just a little bit more, I want to say something about this fair locking business. If you're working with locks, you know, like mutex locks and so forth. This is something that people think about, and sometimes you get this notion of like lock scheduling or lock fairness. What that means is that if you have a whole bunch of threads waiting on a lock, and somebody gives up the lock, the next thread that's waiting gets it. It's kind of like a FIFO queue, or it's like, it's just sort of a queuing thing. This is actually not a safe assumption with the global interpreter lock. It turns out that many of the problems that you have with performance is a result of not doing this. It turns out that performance in Linux is a result of not having a fair lock. So these are kind of the effects that you see with some of that stuff. Like if you look at some of the benchmarks that I gave. One interesting thing that you could look at is you could say, well, why did OS X run so much better than Linux with this Ruby example? 42 seconds versus 5,800 seconds. You could ask a question, which one of those is using fair locking? And it turns out the Mac does treat locks differently than Linux. I did some tests on this, and it turns out mutex locks on the Mac actually do this kind of fair scheduling thing. And you see a huge effect with that there. And the reason that you get a big difference is that the I/O threads actually get their own turn to run at that point. On the other hand, you could go back to this Python example. I mean, back to everybody's favorite platform Windows. Here I showed this benchmark that if you had CPU-bound threads in Python on OS X, ran like 9 seconds. They had on Windows 2008, server, it ran 63 seconds. You could ask the same question there. Which one is using fair locking? Turns out that the Windows is doing fair locking. So now I've got like this really confusing picture. It's like it's good for I/O but bad for CPU. What's happening on Windows here is that it thrashes the system with too much context switching. Python essentially tries to switch threads like every few microseconds, and if it's forced to do that, what you end up doing is like tons of context switching in the operating system. You just kill your performance doing that. And it turns out that all of this fairness stuff is actually something that you don't really want. I'm going to talk about why in a second, but if you go back to this messaging example, one of the things that I showed is that if you had no threads, that test ran in 1.3 seconds. Yet if I had one thread, it ran in 42 seconds. We're still talking about like a factor 33 in performance hit on the Mac, and you can ask, well, why is that? Why is it 33 times slower? And the answer is actually fair locking. I mean, that's why that's slower. But there's actually another effect that's sort of going on there. So I want to talk about one other problem with this GIL stuff. Now I want to go back to this messaging server that was used in this test here. One of the things about the implementation of that is that the server is essentially doing like a receive and a send, something like that. Underneath the covers, it's actually a little bit more than that. I was dealing with messages that had like a prefix on it, like a header. Turns out what it was doing was receiving the header first. Then it received like a payload, and then it sent the header next, and then it sent like the payload. So there's a little bit more sending and receiving that's going on in there. If you go underneath the covers of this, every single one of those operations releases the global interpreter lock. And the reason that happens is they're I/O operations. So there's a potential that they're going to block in the operating system. So you end up releasing this global interpreter lock every single time you do one of those. And one of the sort of pathologies that comes up is that when you do that, if there's something using the CPU, like there's this bad player, the bad Fibonacci thread or something like that, you're going to give control back to that. When you release the lock, you're going to give control back. And what you end up getting is kind of this picture here, where what happens is the CPU-bound thread will run for about 10 milliseconds. Okay, so we're in the Ruby world. It then runs for like a split second to do the receive, and then it basically goes back to the CPU thread and has to wait another 10 milliseconds. So it's kind of almost like a convoying effect, where you're basically blocked by this CPU thread. And what you get is you get these like time delays that add up to about 40 milliseconds in that example. Basically, there's 4 releases of the GIL. Each one hands control back to this CPU thread, and then you have to wait 10 milliseconds. And it turns out that if you look at that messaging test, I was sending 1,000 messages. 1,000 messages times 40 milliseconds is about 40 seconds. And if you look at the result of the test, it was about 42 seconds. Okay, about slightly more than 40 seconds. That's what you're really seeing in that example. There is basically kind of that effect. So you might look at this and say, well, this is just horrible. I mean, it's like, is there anything that you can do about this kind of stuff? And one thing that you might say is, you say, well, just don't use threads. I don't know. What do people feel about thread programming? Is like everybody a fan of thread programming, or is everybody move to async? Is async programming? I don't think this is really a realistic answer. I mean, it's very popular for people to hate threads right now. It's like, oh, threads suck. Hate threads. I think the only reason people hate threads so much is that people are using threads. Like if nobody used threads, nobody would care. I mean, it would be just like a mute issue, and nobody would talk about the GIL or have any opinion about it at all. The other thing I think to keep in mind is that threads are actually used for a lot of stuff. I'm not so familiar with the Ruby ecosystem per se, but in Python you have these different packages like Twisted and these like event frameworks, like G-Event and so forth. A lot of those packages try to avoid thread programming. I mean, they're doing a lot of like asynchronous processing and so forth, but they actually use threads for certain things. One problem in these async frameworks is how do you deal with blocking operations? Or how you deal with like a lot of CPU work. And a very common solution is to maybe like throw that code over into a thread and then like wait for it, rendezvous with it later. You might throw work out to like a different process. Python has this multi-processing module that lets you run things on different CPUs. Turns out that underneath the covers of a lot of that, you find threads. Like Python's multi-processing module uses threads to do monitoring of the remote machine and so forth. So there are threads kind of used behind the scenes. And even if you're not using threads, I think you should still care about them. I mean, like if you're not using them directly, you should still care that they work well because they might be used in ways that you don't expect. And then another thing that you might think about is this other question, and this is actually what I'm really interested in, is can you make the global interpreter lock better? Like making it go away is its own insane problem. I'm not sure that Python or Ruby will ever fully figure that out for the C version of the implementation, but could you just change the GIL? Like could you change it to make it not thrash wildly or do all sorts of crazy things like this? And there have been some efforts in this. So I'm going to talk about what's going on in Python 3 for a second. One of the things that's happened in Python 3 is that they've been moving to a different GIL implementation. I actually find this pretty interesting because the Python global interpreter lock essentially remained unchanged for like 20 years. I mean, it got introduced in 1992, and then it went completely unchanged until about 2010. Okay, so this is when this work in Python 3.2 started. So Python programmers actually started thinking about this. It's like, can we make a better GIL? It's not perfect. It actually has some of the same problems that the Ruby GIL has. What Python is doing is they've sort of switched to a timeout-based scheme. So they've actually abandoned that whole tick counter business. They've sort of said, well, that was maybe kind of stupid. So that they've sort of gone to sort of a timing based thing where the way that it works actually is a thread, when it wants to get the global interpreter lock, will wait up to 5 milliseconds to get it. So what it does is it enters this kind of wait phase and says, okay, give me the lock. I'm going to hang out for 5 milliseconds. If it doesn't get it, it forcefully preempts the other thread. Okay, so it's sort of a timing scheme. Unfortunately, it has the same issues that Ruby does, that it kind of presented. It's essentially you get these 5 millisecond delays in your code, and you can actually sort of see that in some of the benchmarks. This is going back to one of the earlier tests. If you run Python or Ruby with no threads on this messaging thing, it takes about 1.3 seconds. If you run with Python 3, it takes about 20 seconds. If you run it with Ruby 1.9, it takes about 40 seconds. And you can say, well, what's the difference between Python 3 and Python and Ruby? 5 milliseconds. That's the difference. I mean, it's sort of the delay is about half in Python as it is in Ruby. So that's what you see there. So some other things that are kind of going on in the Python world. This is not anything that you can find implemented in the Python core right now, but there's a number of people experimenting with priority scheduling. Again, I'm not a Ruby expert, but it looks like this was actually something that was done in earlier versions of Ruby as well, with Ruby 1.8, green threads, and so forth. Essentially, you had this ability to set like a thread priority, and what you can do is kind of crank up the priority of like I/O threads or CPU-bound threads, and you can actually get this, get the performance to run better. You can actually see this in Ruby now. If you run the CPU thread but lower its priority, and you run it in Ruby 1.8, it actually runs better. I mean, the lower priority does affect things. And people have been messing around with this in Python as well, messing around with some priority schedulers. One of the things that people are doing in the Python world is kind of experimenting with priorities, but this idea of like immediate preemption of things. And the idea there is that if a high priority thread wants to run, it just immediately steals the GIL. doesn't even wait around for it, just immediately takes it. If you do some of that, you actually get some really nice results. This is something that I've been playing around with. If you run with that messaging test with priorities, you just completely eliminate that 5 millisecond delay, and you actually get results that are sort of comparable to C programming. So there is some promise there. Priorities have their own set of problems. Just as a little bit of backstory, at the PyCon conference 2 years ago, when they were talking about this global interpreter lock stuff, there was an after-hours session that I led that had, so Guido van Rossum came to that, and a whole bunch of other people showed up. I don't know why they were at a PyCon conference, but there were a whole bunch of people who had actually worked on operating system kernels. Maybe they'd like burned out. They're like, to hell with operating system. I'm going to go program Python because it's so much enjoyable. But they sort of showed up at that, and there was this huge debate about priority scheduling and, like, kernels and like what you want to do and like all the problems, starvation, priority inversion, all the implementation complexity. One of the fears in the Python world is if you're going to do priority scheduling of threads, do you have to implement your own operating system? Like, if you know anything about operating system scheduling, it can actually be very complicated. I mean, all these like all these different priority levels and raising priorities over time and like feedback queuing and all this other stuff. So the Python programmer, like core developers, are actually legitimately concerned. Do we have to write an operating system in Python to do priority scheduling of threads? And that's sort of an open question. Has not been resolved. So I did get the 10-minute signal up here. So just a few final words on this. What I'm hoping to do in this talk is to really just kind of throw this idea that you can fix the GIL, or that there might be ways to fix it, but implementing a global interpreter lock turns out to be really tricky, or a lot trickier than you might think. It's way more tricky than just putting like a mutex up there and just saying, oh, there's your lock. There's other issues to kind of think about. The other thing that I love about this is just how diabolical multi-core is. I mean, if you think about like having 8 CPUs on your machine, they're all fighting over locks and things like that. It's sort of a diabolical problem. I think it's actually something to think about if you ever hear about people like wanting to eliminate the GIL entirely. Like if you're going to take Python and make it fully free-threaded on like multiple cores, I sort of wonder, like, well, how complicated would that get, considering how complicated this is? I mean, is that more complicated? Is it less complicated? Not really sure. So that's kind of the end of the talk. I know that might have gone really fast, but I hope that you learned at least one thing in the talk. I'm very interested in just sort of feedback on this stuff. So if you have ideas, send me an email. I can also be found on Twitter, sort of the one bullet point of self-promotion there, I suppose. So, okay, so I think that's it. Actually, one thing in the this is sort of amusing. I was going to put it in the slide earlier. Let me see if I had it on my flight over here. I don't know if you can see that. I sat next to somebody named Gil. There she is. It was like I'm sort of known in the Python world as being like fixated on the GIL, oh, Beasley, it's a GIL. So I come over here, I'm like sitting next to somebody named Gil, and I actually told her about this talk, and it turns out that she used to teach computer science and math, right? So it's like knew all about it. I'm like, yeah, okay, so very, what? What are the odds? Yes. Very weird. So I think we have some. Where did my timer go? Do we have time for a few questions? Is that okay? We have questions. We have one over here. Okay. I'm pointing. You have a question, yeah? Oh, you're waiting for a mic. Okay.
So I have got 2 questions, kind of related to your talk.
Okay.
Yeah, because you talked about GIL, and I'm really scared about the performance considerations here. So I'm excited about the PyPy's team announcing research on software transactional memory, and I would like to know your opinion on that. And the second question is, if the GIL is such a problem, why not abandon it and replace it with green threads or some even threads or something like that.
So the software. So do people know about the PyPy project? Everybody knows. So the PyPy project is it's Python written in Python, and they're doing a lot of work with like just-in-time compilation, JITs, things like that. Actually runs significantly faster than CPython. Although ironically, that messaging test that I did where it was like where Ruby was like 5,000 times slower, that's what PyPy does, by the way. They fixed it, but it's this version of Python that runs a lot faster. They've been talking about this idea of using software transactional memory as a programming technique. I'm not sure that that's actually addressing the exact same problem of the GIL. I mean, I could be wrong about that. I've sort of read what they're proposing. What they want to do is essentially have like software transactional memory as maybe like a programming model for users to do concurrency, or basically being able to support that as like a supported way of doing threads, and maybe using it at sort of that level. The thing that I'm not sure about is whether they can make the underlying implementation of PyPy thread safe. That's kind of what the GIL is related. It's a very low-level implementation detail of the Python interpreter itself, and I'm just not sure that how they're gonna address that. I mean, PyPy actually runs on top of a variant of Python called RPython. I don't know how it ties into that, so I don't know whether that's a great answer to your question. Actually, what I want to do. It's not going to work because I'm going to fess up what I'm doing. I actually want to tell the PyPy guys that it's actually impossible so that they will prove me wrong. But since I just told you that I want them to prove me wrong, I sort of invalidated that, you know. But yeah, you just need to tell like a motivated grad student that it's impossible, you'll never get it to work, and then they'll go off and do it. The second part about the green threading thing, that's kind of a tricky thing. I mean, I know in Python, the reason they use real threads is that a lot of people use Python with C extensions. And in C code, you can actually release the GIL and run fully parallel. A lot of people do that with like scientific calculations, big number crunching things. I'm actually a little bit curious, maybe to talk with some of the Ruby people later, because my impression is that Ruby had green threads and then just recently moved to system threads. And I'm sort of interested, like, why was that decision made? I mean, what sort of motivated that? I mean, maybe you don't have to answer that now, but I could grab somebody later. But okay.
Hello. I'm interested in the idea of removing the global lock, and I do not know details about the implementation of neither Python or the Ruby, but it would seem that there is not too many of those critical places that where you really need to ensure that there's no concurrency going on. So I just want to ask if you know how many places are we dealing with, or is it just a few critical area of some shared memory access, or is it like everywhere?
Okay, I can only answer that for the Python side. Actually, as a point of curiosity, the GIL was actually removed in Python in 1996, in Python 1.4. You can say, well, how come it came back? Okay, so the details of that patch, there's actually sort of three main things that they did. They had to put locks around all reference counting operations. Python uses ref counts for memory management, and it turns out that that's a pretty bad way to do memory management for threads. So you have to put locks around through all the ref counts. They had to put some locks around some internal data structures in the interpreter. Python does some things underneath the covers, like it like caches previous values, internal like little memory management things. They had to put some locking around that. The other thing that they had to do is add locking to all mutable data structures, meaning lists and dictionaries. So because you had problems like, a thread could maybe add to a list at the same time another thread was like resizing it or something like that. So those are sort of the three things that happened in that patch, is like locks around ref counts, locks on mutable data structures, locks around some internals. It was actually not a big patch. I've actually looked at it recently. It's about 1,000 lines of C code that got changed. Python 1.4 at that time was maybe 80,000 lines of code. So you're looking at 1,000 lines of code. The thing that really killed it, the performance was terrible. It ran like 2.5 times slower. on Windows, and I think on Linux it was 6 times slower. The thing that really kills it is the ref counting. If you put, I've actually done some experiments with that recently, just like taking all the ref count operations in Python 3, if you make them atomic to do thread safe, it just runs twice as slow right out of the box. And that actually turns a lot of people away because there's quite a few people who use Python without threads, and they're like, why would I want a 2x performance hit if I'm not doing thread programming? And so that might be more than what you wanted to know, but then.
I have the question why the GIL is not per CPU or per core. Why it's, you know, you have 7 cores and you run 7 times Python interpreter and it works like that.
You know, I don't know. I've heard that. I mean, you know, this idea, if people know what he's talking about, essentially the idea is you might run like 7 copies of the Python interpreter in 7 threads in the same process. I certainly don't know for Ruby. I know in Python it's a little bit tricky because there's a lot of global data structures in the C implementation. So it's not so straightforward to isolate the interpreters in that manner. You would still have to have some lock on that. Actually, as a kind of a side note to that, the effort to make Python, to get rid of the GIL in 1996 was actually aimed at doing almost exactly that. The guy who did the patch was actually trying to get Python to play nice with IIS on Windows. This is kind of going back a ways, but they're essentially doing web programming on Windows with IIS. And he wanted to basically have like different threads being able to use the Python interpreter at the same time without the GIL. So that's actually where that patch originated, was to do something very close to what you just asked. Okay. Any more questions? There was one that had their hand, somebody had their hand up, but maybe I just answered the question there.
Thank you, Dave.
Okay, thank you very much.